last part before I go on to the next presentation, that is 2 samples, is remember most often we assume that the underlying population distribution is normal, right, either for a t distribution or a chi-square. Our underlying population distribution is normal, and test for normality is a common task. Okay. If you know that the underlying population distribution is normal, there are several things, theorems and useful things that can be done. So it is very important, or most often you test for normality of the underlying distribution. Okay. So how do you go about doing it? How do you test that, you know, my data is, whatever data I collected, it is normally distributed? How do I test it? If I have large number of samples, then I can plot the data and frequency histogram, but what if it is small, or what it is not enough? How do I check? So that is where you call what is known as a probability plots. It is a visual way, there are theoretical way, I mean there are statistical ways to verify whether the underlying distribution is normal or not. Here we are not going to do it, we are going to use a simple mechanism to understand whether the underlying distribution is normal or not. It is called probability plots, using a simple idea. So how do I do? To construct a probability plot, the observations in the sample are first ranked from smallest to largest. So rank the observation values from smallest to largest. Okay. x1 to xn is arranged to where x1 is the smallest observation, x2 is the second smallest, and xn is the largest observation. Okay. Now the ordered observations are then plotted against their observed cumulative frequency. What do I mean by that? Why is it too late? Next time make sure you are not. Okay. So the ordered observations xj, this is my ordered observations, are plotted against their observed cumulative frequency j minus 0.5 by n. You know what is j? J is what? 1, 2, 3, 4, 5 etc. Okay. And j minus 0.5 by n, that is nothing but my cumulative frequency. How it keeps on increasing, right? What is, so the idea is pretty simple. You have the cumulative distribution plot for cumulative distribution for a normal distribution. Do you have a cumulative distribution for normal? This is my PDF. A PDF of a normal distribution is what? Sorry, it's a bell shape. Now can I do a CDF for this graph? What is CDF? How will it look like? It is increasing first initially slowly, then rapidly, and then somewhere it will have a saturation, because this is addition of this CDF. Now if the idea behind this plot is very simple, if your data, if your underlying data is normal, it should have the same CDF as that of normal distribution. You understand? If your underlying data, see PDF is you have to plot a large amount of data, CDF is what? I am accumulating the, I am adding the probabilities and then plotting it. If I plot this and if I plot the normal, they should look like same, right? If your underlying data is normal, then the CDF of normal distribution and the CDF of your data should be the same, right? Now how do I validate, how do I verify that? So in one end you have xj, on one side you have xj, then the other side you are plotting the cumulative frequency, that is j minus 0.5 by n. 0 to 1 is the total probability. Okay. So j minus 0.5 by n, 0.5 is the center, this side and this side 1 over n. Okay. So keep adding, keep plotting it. So this is plotted on a special plot called probability paper, on an appropriate probability paper. This is probability paper is available for normal distribution. So you can Google, you will see what is, how does a probability paper look like for normal distribution. The simple idea is how much percentage of data will be between 0 to 25 percentage, how much data will be between 25 to 50, 50 to 75, 75 to 100. Now if you plot your data on this probability plot and if it turns out to be a linear line, then you can safely say that your distribution is, your data distribution is normal, okay, right. Y equals to mx, you should have a straight line because they are highly related just with the slope value, right. Y equals to mx, if you plot y and x it will be, so that means what, y highly resembles x with a just a slope factor. In this case the slope factor is also taken care of the plot only. So if you plot your data in this fashion, a probability plot, if it turns out to be linear in the probability paper, then your distribution is normal. The idea is comparing the percentage of data below 25 percentage, below 50 percentage, below 75 percentage from your data against the standard normal distribution. The idea is comparing the cumulative distribution values. How much percentage is below 25, how much percentage is below 50, how much is below 75, how much is below 100. So you keep plotting that, and in the probability paper, then if it matches that of the standard normal, it will turn out to be a linear line. That will tell you whether the distribution is normal or not normal. This is your normal probability plot. See if it is, so if I have my cumulants also to be same as that, then y and x will be highly related, right. That distribution and this distribution should be related. That is why I said y equals to mx idea. So your data should highly resemble the normal distributions cumulative plot. That means y and x are highly related and there should be a linear relation, y equal to mx, that is what it is. Clear? So this is a probability plots, okay. So a normal plot can also be constructed by an ordinary graph paper. This is what you should be using, very simple. It can also be done in an ordinary graph paper by plotting the standardized normal scores zj against xj. So this is my xj and this is my zj. So we all know what is xj and zj is what, you know, minus 1.65, 1.65, this is nothing but j minus 0.5 by n, probability of z less than or equal to zj is phi of j. So okay, so for example if j minus 0.5 by n is 0.05, look for phi of zj, implies this phi of zj 0.05, we know what is this, 1.64, 95 percentage, 1.64 minus 1.64, that is what here is. So this j value corresponding, the value corresponding to j here is 1 minus 1.65, you understand. So you have did the same, xj is arranged from the ascending order, you have plotted xj, okay, and on the y axis you plot phi of zj, where zj is nothing but j minus 0.5 by n. This is your standardization basically. Your variance is assumed to be 1 over n, where mu standard deviation is n and your mean is 0.5 because probability is 0 to 1, so mean is 0.5 and then your variance is 1 over n square and standard deviation is 1 over n, that is what you did, okay. So this is what you have. So phi of zj. Now if you plot this in an ordinary graph paper itself, you should get a linear line. So this tells you that below, this line tells you that the cumulative distribution of your underlying data, what you get is same to that of the normal distribution, standard normal. Make sense? Okay. The only transformation in an ordinary graph paper is you are doing a phi of zj, okay, clear? Any questions? Shall we move on? So this is our probability plot, simplest way to ensure that your underlying distribution is whether normal or significantly non-normal. okay. It may not tell you close by etc. Either it is not normal or significantly not normal. Okay, if this graph is going to be exponentially increasing decreasing, then you know that the underlying distribution for sure is not normal. Okay. These are some cases where you can clearly say that the underlying distribution is not normal. The straight line should have been like that, but you have so whether there is more data to the left or more data to the right, all of this can be got from this idea. Okay. So what is p value before we move on? 1 minus p percentage is the percentage of confidence with which I can reject the null hypothesis. Exact confidence with which I can reject the null hypothesis is nothing but 1 minus p percentage. Okay. So that is where p value becomes important. Okay. So now the natural step going forward is we have did hypothesis testing for one variable, we should be thinking about extending it to 2 variables before we extend it to multiple variables. Okay. So the next step is to do 2 variables, but before we do that, since we have talked about probability plots, there is one more test which may come in handy. Okay. That actually 2 tests we will look at one by one. The first test is test for underlying distribution. So far what we have done, we have discussed about what? The probability distribution is known, population or probability distribution is known, the hypothesis involves the parameter of the population distribution, right. So you know the underlying population distribution or you know the sampling distribution, and then you are testing about the parameters of the distribution. That is what we have been doing for both mean and variance. Now we might wish to test the hypothesis that the population is normal or go binomial etc. So in this case we do not know the underlying distribution and we wish to test the hypothesis that a particular distribution will be satisfactory as a population model. So in this case our hypothesis is on what is the underlying distribution itself. You understand what is the possible underlying distribution of the data. Okay. Probability plots is only one way to see whether it is normal or not normal. I want to know what is the underlying population distribution, most likely population distribution. Okay. That is the test we want to do, that is also called testness for goodness of fit, test for goodness of fit. So this is something which you will encounter in your when you do experiments, they call it as goodness of fit. How good is your fit basically. Okay. So goodness of fit test is something very commonly used. So the procedure, if you go through, it requires random size from sample n whose probability distribution is unknown. So you do not know the underlying population distribution, you take n samples. These n observations are arranged in a frequency histogram. So we know what is histogram, so we arrange it in a histogram fashion having k classes or intervals. Let OI be the observed frequency in the ith class interval. So OI is the observed, and what is EI? If OI is the observed in the kth class, what is EI? Expected what? Expected frequency depending upon the distribution that we assumed. So what am I assuming here? I am saying the underlying population is, let us say, Poisson or normal or gamma or t square, t or chi square, whatever, right. Now if you assume that for each bin, because your frequency, your probability is now entirely divided into multiple bins, right, frequency histogram you are dividing it, you know in each quartile however what is the probability of, that is expected frequency, and you know what is the observed frequency, in each class. So what are we doing? These n observations are divided into frequency histogram having k bins. So there are k bins or class intervals. In each interval, based on your data you will get an observation, that is your OA. In each interval, based on your assumption of the probability distribution, you will get a value that is called expected. So we are going to calculate observed minus expected the whole square by expected. Notice this should be, this is a squared deviation, we are talking about squared deviation, how much my expected and the observed are deviating, squared value, this should follow what? Chi-square distribution. This should follow a squared deviation, should follow a chi-square. So this is assumed to follow a chi-square distribution. Okay. Let us take a simple example, then you would know this. So I am saying the number of defects in printed circuit board is hypothesized to follow a Poisson distribution. So we are saying because in a PCB it is very rare to have faults today, it is not a common event to have faults in a PCB, right, well you are doing manufacturing it. If I have more faults then there is a huge loss, so it is usually assumed to be a Poisson distribution. Okay. Now a random sample of n equal to 60 is taken and the following number of defects are affected. So 60 PCBs are taken, the amount of time 0 defect is there 32, 1 defect 15, 2 is 9, 3 is 4. Clear? This is my observation. I want to know whether this data follows a Poisson distribution or not. You understand the question? So I have PCB boards and PCB boards can go faulty, it is usually a rare event, so I assume that it is a Poisson distribution and my observations are given. When you talk about Poisson distribution, what is the parameter? E to the power minus lambda by e to the power minus lambda into lambda to the power x by x factorial or something, right. So now lambda is the unknown parameter which is the mean and the variance both NP and NPQ. So I do not know the lambda of the unknown parameter, unknown distribution, lambda is unknown to me for the Poisson distribution. I can calculate lambda from the samples, right, I can calculate lambda from the samples, lambda is nothing but mean. So the mean defects is how much? How do I calculate mean defects? It is weighted with probabilities, right, weighted. So 32 into 0 plus 15 into 1 plus 9 into 2 plus 4 into 3, the total number of defects is weighted average. Okay, 32 times I got 0, 15 times I got 1 defect, so 15 false, and 9 into 2 plus 4 into 3 divided by what is the total n? 60. So I have the average defect, this thing to be 0.75. So lambda is 0.75. So far so good, right. I have a table of faults, I want to know whether this data follows a Poisson distribution or not. I do not know the value of Poisson distributions parameter, so I assume it to be from the data itself, its lambda equals to 0.75. From the if you assume the probability distribution is Poisson, if the underlying probability distribution is Poisson, what is the probability of getting one defect? E to the power minus lambda into lambda to the power 0 by 0 factorial, right. The formula is Poisson distribution is e to the power minus lambda into lambda to the power x divided by x factorial, x here is number of defects. So I have a value for 1, 2 defects, 3 defects and 4 greater than or equals to 3 defects, right. So now my number of defects, what is the probability for 0? 0.472. What is the expected frequency? How do I get expected frequency? 0.47 into 60. Similarly 1 defect, 2, 3 or more, and this is my expected table and this is my observed. So I have expected, observed 32, 15, 9, 4, 28, 21, 7, 2. Okay. So now I can compute a simple test to make sure to be sure whether the underlying distribution is truly Poisson or not, right. You have been given a data, you have asked whether this is a rare event or not, that is the question we are asking. Okay. It should be ideally rare, is it really rare as per the data, that is the question. So what did we do? We know rare event is Poisson, so we know the probability distribution. Of course lambda is not known, so we calculate the lambda from the data itself, and then you have now a expected table and observed table, and now you can formulate the hypothesis testing. What is the hypothesis? The variable of interest is in the form of defects. The form of H0 is what? Poisson. H1 is not Poisson. 95% confidence. What is the test statistic? Chi-squared. Square deviation observed minus expected the whole squared by expected. So, this is nothing but goodness of fit. That is why it is called as goodness of fit. We are fitting a distribution to the underlying data. So, it is a goodness of fit. So, compute it, you can make the assumption. In this case, you are unable to reject the null hypothesis. That means it is following a Poisson. At least you are not able to say that it is not following a Poisson. You are not able to reject the null hypothesis. So, you can do the computations. Clear? Goodness of fit. Do you want to do this problem? Okay. Unless you do it, it becomes difficult. Okay. Can we do this problem? Everybody able to see the screen? So, this is the problem statement. Okay. A manufacturing engineer is testing a power supply used in a notebook computer, and using alpha equals to 0.05 wishes to determine whether output voltage is adequately described by normal distribution. So, I want to say whether the underlying distribution is normal or not. Okay. Sample estimates of the mean and standard deviation are x bar and s is given and are obtained from a random sample of n equals to 100 units. Okay. So, unlike previous case, I have given you the mean and standard deviation of the data estimates, okay, and the number n also. So, this is all the problem statement. The other statement is actually the solution. Okay. This is the only problem statement. Okay. So, problem statement is very simple. The manufacturing engineer has designed a power supply. He wants to know whether the output voltage is a normal distribution, which is important, right. It will be noisy. You have to tell me what is the mean and what is the standard deviation of normal, the standard deviation and approximate distribution, right. You cannot get a constant value, right. So, you are saying it is a Gaussian distribution with mean 5.0 volt and standard deviation is 0.08 volt, and he has got this data from, he has got these values from 100 units by conducting test on 100 units. Now, how do you test this hypothesis? That is all the statement is. How do you go about doing this? I have given you x bar standard deviation and n, and I am asking you whether the underlying distribution is normal or not with alpha equals to 0.05 or 95% confidence. How do you go about doing it? Any thoughts? You understand the question? I have this mean value, variance value, and for this n data and 100 units, tell me whether my distribution is normal or not. That is all he is asking. How do we start? Where do we start? So, in the Poisson distribution, what did we do? E to the power minus lambda into lambda power x by x factorial, and then we said what is the probability of 0 defect, 1 defect, 2 defect. How do I do the same here if I want to do? So, I can assume this to be mu and sigma, okay. I can assume my x bar to be mu, I can assume my s to be sigma, then what do I do? I have to divide the data into intervals. Remember, this is a continuous distribution, this is not a discrete distribution. So, you have to have class intervals, and remember what is your x bar is 5.04, okay. So, a common practice in constructing the class intervals, the cell boundaries, so that the expected, so you have to have boundaries for a standard normal distribution, okay. So, let us say suppose we divide it into 8 cells, we are going to divide it into 8 cells, it is up to you to choose the number of cells. Remember, you have to discretize, you have to find out regions, it is not a point, because the earlier problem we had a point because that is a Poisson distribution, it is a point, right, it is a discrete distribution. Here the values span from minus infinity to infinity. It is truly a continuous distribution. Suppose I want to divide it into 8 cells, 8 intervals, like in your normal distribution how much they would have divided, 0 to some 3.3, that is all the range, right. So I want to divide it into 8 cells. How am I going to divide? For the standard normal distribution, the intervals that divide the scale into 8 equally likely segments are, okay, 0 to 0.32, 0.32, 0.65 up to 1.15 to infinity. How did I come up with 1.15 to infinity? How did I divide it into equal? 0 to 0.32 is what? If you go back to your normal table and look at it, 0 to 0.32 value will be same as 0.32 to 675, 675 to 1.15 and 1.15 to infinity. This is the accumulation of the CDF values in this range, 0 to 0.35, 0.32 to CDF, 0.32 to 0.675, 0.675 to 1.15, 1.15 to infinity. This is the CDF values. The values within the CDF value within this range is all are same. I am dividing the interval into 8 equal cells. Okay, so let's take this. I am dividing this entire interval into 1, 2, 3, 4. Yeah, 1, 2, 3, 4, 5, 6, 7, 8 equal segments. Say 8. Okay, I am dividing the entire normal distribution into 8 equal segments. Okay, I have taken 8, you can do 10 or you can do 5, etc. So what is the idea? The observed in this should be equal to the expected. You are going to look at the observed minus expected the whole square. That is what you are going to do for fitness. So I am first doing the theoretical, right. So now I have divided into 8 equal intervals. For each interval the probability value is what? 1 over 8. So what is the expected value? Expected value is NP, right. We know what is mean. Mean is NP, variance is NPQ. For this is like binomial, but then we are making into classes. That is why NP, expected equals to NP. N is given to you 100, 100 into 0.25, 0.125 is 12.5. So 12.5 is the expected frequency for each class, because it is the same, it is all probabilities are 1 over 8, because you have divided into 8 equal classes. So 1 over 8 is the weightage, 100 is the number, so all expected frequency is 12.5. What is the observed frequency? How did I get these numbers? How did I get these numbers, observed values? How did I get these observed values? I did not give you the numbers. How did I get these? They did not give you, the problem statement is only this. How did I get these observed values? Use first standard normal, make a z out of this. Z equals to x bar minus mu by sigma, right. So you actually have this, convert this into x minus. So this x bar is known to you, s is known to you, right. So given the x bar and mu, you can convert it into a standard normal. Standard normal, z equals to x minus mu by sigma. You take this as the x, this as the sigma. So z equals to x minus mu by sigma, or x bar minus mu by sigma over root n. You can standardize this into a z star. You understand what is z? Z equals to x minus mu by sigma. In this case x is nothing but x bar, so it is going to be x bar minus mu by sigma over root n. Now you have standard normal. Okay, now you have standard normal between 0 to standard normal 0 comma 1. Now what is the value? So you have x here, okay. So you have what is the observed frequency for after converting z equals to x bar minus mu by sigma over root n. Look for x, substitute x equals to 4.98. I do not know whether you remember this, let me show you. I see a lot of faces, Let me show you the normal distribution. The problem what we have solved. Did we not solve this? What is the probability of x lying between 2 to 4? How did we solve this? X is approximately normal 5 comma 2. Here what is x approximately? Normal 5.01 comma whatever standard deviation given to you. What is the some volt? 0.08 volt and then 5.0 volt, that is what. So x follows normal 5.0 volt comma 0.08, and what is the probability of x less than 4.998? You can compute it from the standard deviation. Can you not compute it? You understand or no? What am I saying? On one end, for x expected, you divided the normal table into 8 equal intervals. Okay, you computed the mean to be 1 over np, which is n into 1 over 8, because all are equally likely. So the frequency in each class each is what? 0.125. If you would have divided into 10, what you would have got? 0.1 in each class. That is my expected. What is my observed? My observed, how do I calculate? What is given to you observed? X bar is given to you, S is given to you. Assume that as the population mean and population standard deviation. Remember in the last problem what did we do? We calculated lambda from the data and we assumed it to be the population. Similarly x bar is to be mu and sigma is S is to be sigma. So you are given x bar is given to you, that is mu is given to you, sample standard deviation is given to you. So if you square it you get the variance. Okay. Now so you look at this parallelly here, right. So this is what I was talking about, probability of x taking on between two values. How did I compute it? Standardize using your mu and sigma, make it to standard normal, look at the tables and compute it. Similarly what do I want? I want x less than 4 point some number, because you have divided into 8 equal classes, right. So you look at this number, so you will have what is the frequency, that is 12.5, and then 4.948 to 4.986. So you start dividing it into class intervals so that their probabilities are equal. Your observed frequency, this is computed from standard normal tables into 100 observed, compare expected and observed. Go try solving this problem. I thought I will not even explain, but now I have explained. So compute how do I get the observed frequency, expected frequency I have given it here. Go compute how to calculate the observed frequency. Mu has to be assumed to be 5.04 because x bar is only known, mu is not known, right. So what will I do? I have to assume the mu to be 5.04 because I am assuming whether the population underlying distribution is not normal or not. I have given only the sample parameters. I will assume that to be the population parameters and then say whether the underlying distribution is normal with mean as 5.04 and standard deviation is 0.08 or not. That is the question. No, it is not x bar minus mu. That is why I said look at the right hand side, x minus mu by sigma directly. Your S sample variance will become the population variance, sample mean is assumed to be the population mean, and x less than 4.98 is nothing but 4.98 minus 5.01 divided by 0.08, that is the z value. Now look at the z value, look at the probability values, multiply it with 100, you get the observed. Compute observed versus expected the square deviation. Okay. So go look at this, there are some more catches in this problem, go look at it. Okay, I have not explained fully, so please look at this carefully. Any questions? The only catch, I think I have written it here, damn. The only catch here is how did I get 4.948 as the beginning step? Okay, this okay, got it. It's on x bar 1, that is all. Huh? x bar minus 1.15, you are dividing into class intervals, right. So 1 minus 1.15 times sigma plus 1.15 times sigma as the extremes, that is all. X bar minus 1.15 times standard normal, right. Now standard normal you have divided into 8 classes, right. So what is the relation between standard normal and this thing, z equals to x minus mu by sigma. So what is this thing, x minus mu equals to sigma z, x equals to mu plus sigma z, that is all, right. So that is what I have, x minus, so our mu equals to x minus whatever, rewrite this equation, z is there. So now you know the z value 1.15, you have divided into 8 classes, sigma value is given to you 0.08, that is nothing but sigma is replaced with s, okay. So look at this, on the other side extreme it will be x bar plus 1.15 times s, understand. How did I get, so in the last problem, how did I get x less than 4.998, this one, sorry, how did I get this, I know I am going out, sorry, x is 4.998, how did I get x less than 4.994, I divided the standard normal into 8 intervals, right. The 8 intervals are nothing but 0.32, 0.675, 1.15, infinity on one side, on the other side also it is the same, it is a mirror image. So 8 classes. Now how did the class interval for x start from 4.948? This is the relation, this is standard normal pa, standard normal is x minus mu by sigma. So what is the class for x? X equals to sigma z mu plus sigma z, that is all. What is the mu value? 5.04, that is what we have assumed, right, 5.04, 5.04, and what is the sigma value? Sigma value is point, and what is the z value? Minus 1.1, minus 1.15, that is the beginning, 8 classes, right, 4 on the negative, 4 on the positive. So minus, compute this, 5.04 minus 1.15 into 0.8, what is the value? What do you get? Not able to compute, 0.08 into minus 1.15, 4, that should be definitely 4 point, but what is the exact value? This is what we have, that is the starting point, 4.948. So the region from minus 1.5 to infinity to minus 1.5 is nothing but x less than 4.948. And what is the region between 1.15 to 0.32, I mean minus 1.15 to minus 0.675, substitute the values, you will get the same. That will be between 4.948 to 4.986. How did I get 4.986? What is 1.15? 0.675. Substitute 0.675, you will get the answer. 5.04 plus 0.08 into the second bin is minus 0.675. I am talking in the negative side, so it is minus 0.675. What is the value? 4.986. You look at the second value, this is 4.986. That is the second bin end. What is alpha? I am not. That is 95%. That is for testing of confidence. That is when I conduct the. No, but my hypothesis on the deviation. First I have to compute the deviation, na? Where am I computing the deviation in the first place? Observed minus expected, where am I computing? No, we are talking about the overall. So if I am expected value in this region is what? Observed value in this region is what? That is the question. You have asked normal distribution, right? Underlying distribution is normal or not. What is the expected value if it is normal distribution? What is the observed value if it is normal distribution? Then combine both, take a deviation and then see observed minus expected the whole square whether it is truly. So expected if it is a normal distribution you know, observed you know, compare both. If the deviation is small it is going to be null hypothesis is true, otherwise alternate hypothesis. That is what we have done in the last. The last problem was very easy because it was only discrete distributions. So lambda was calculated from the data, you substituted lambda, you saw the probability of defects, observed is given to you, okay, observed is given to you, only you calculated expected. In this case observed is not even given, instead of observed they gave you x bar and yes, you have to assume it to be mu and sigma, okay. And now how do I calculate expected? You divide the entire normal distribution into standard normal into x intervals. In this case I have divided into 8, if you divide it into 10 it will be 10 intervals, okay. And how do I compute the expected value? Expected is given. How do I compute the observed values? The observed values you have to compute from the normal distribution with mean mu equals to 5.04 and standard deviation equals to 0.08, okay. But that you cannot integrate it, that is a catch, that is why this problem is slightly complex, you cannot integrate it. So you have to make it into a standard normal, right. So your standard normal probability of 1.15 corresponds to x value of 4.948. Your standard value, standard normal 0.675 corresponds to an x value of 4.986. Like that you have to get these values. Now this is the class interval, this is my expected. How do I get the observed? Again make it into a standard normal, look at the standard normal values and fill these values, NP, okay. You will get the P, multiply with N, you will get the NP. Now observed minus expected the whole square. I have divided the entire standard normal into 8 equal intervals, 8 equal intervals. So the CDF values should be equal in each range. So if you look at CDF of 0 to 0.32 and 0.32 to 0.675 they will be same. So you divide the entire probability CDF into 8 equal half bar. You see what I mean? The mass, so that is what I said. So this is my entire PDF, right? So this is my CDF. If I sum this up to this is my CDF. This CDF and this second CDF should be same. Second CDF and third CDF should be same. Third and fourth, like that you divide it into 8 equal intervals. It is easy if you divide it into 8 equal intervals because the weightage is going to be, P is going to be 1 over 8, okay, probability, because all are equally likely. So NP is going to be 1000 into 1 over 8. If you do not divide it into 1 over equal intervals then probability cannot be 1 over 8, so then you will have to break your head, okay. So that is why I have broken down the CDF into 8 or x equal intervals. Then your probability is simply 1 over n, all terms are equally likely, all regions are equally likely. Divide the CDF or take the intervals such that all intervals are equally likely, then your probability is just 1 over n, I mean probability is 1 over the number of classes. If you do not do that then your weightages will change, you will have to break your head. So your expected frequency is what? N into P. How do you compute P value if I do not divide into equal intervals? That is a challenge, okay. Table, I have to know that you look at the table and divide it, that how did I get 0.325, go and look at the table. okay. So this problem is tricky, it involves enough steps, tested you enough. So you have to know first of all how to compute expected itself. Expected itself is not straightforward, dividing into equal, NP has to be applied, and then observed, even more trickier bit, right. Then if you compute both, then it is very easy, it is standard normal. Chi-square is test is very simple. Once you have both, then what is chi-square? Observed minus expected whole square by observed expected, you put this n minus 1 degrees of freedom, all good things come out, but it is not as easy, the both computation, okay. So please pay attention to this problem and try to solve it.